welcome to the first session of Binder Group's new technical webinar series. Today we're going to take a closer look at what variable springs are, and we're going to have a look at these in a bit of detail. So joining me, I've got Roger Shemilt and Brad Pearce. Brad is our senior engineer. He's been with Binder since 2003 and joined Swift Metal when Binder was acquired in early 2024. With more than 2 decades of hands-on experience, he's widely regarded as our resident pipe support expert, deeply familiar with the design, engineering and real-world application of variable spring supports, and brings an enormous amount of practical insight to today's session. Roger's our technical director. He's been with Swift Metal since 2001 and has worked with pipe supports in every stage of a project, from design and engineering through to manufacturing. He has an exceptional understanding of how supports behave in the field and what's required to make them reliable, durable and easy to maintain. I joined Swift Metal in 2023 as a specification consultant and work with the engineering teams during this design and specification phase of major infrastructure projects. I typically work with both Roger and Brad to ensure that our clients receive practical solutions that perform in the field. There's 2 key questions we're here to answer today. The first is around how to choose the right size and type of spring support. And the second is how to verify if they're performing correctly. In answering the first question around choosing the right size and type, we're going to look at the different spring types, which each is used for, how to choose between hanger and base mounted designs, the information you need to size them correctly, and then the 25% variability rule. We're also going to cover off on travel ranges, material options, and corrosion protection so that you know how to specify the right configuration in your environment. For the second question on checking performance, we'll look at what correct movement looks like, how they should be installed and set up, how to read the load indicators, and the typical signs that something isn't performing the way it should. We'll also touch on basic maintenance and safety, because that goes hand in hand with performance. With that in mind, we're going to begin by looking at how a variable spring support functions. Before we get into the details, it's important to understand how a variable spring support works. So this diagram gives us a bit of a breakdown of its individual components. Overall, the spring is designed to do 2 things. It's there to allow the pipe to move and ensure that the pipe is supported through that range of movement. Those 2 requirements generally can't be met with a rigid support because any vertical movement usually overstresses the pipe or overloads the support. A variable spring solves this problem by using a helical coil inside a steel casing. That coil compresses or relaxes depending on the direction of movement, which lets the support carry the load while still giving the pipe freedom to move. Every Binder variable spring support comes from the factory in a preset condition. They typically set at what we call the cold load, which is the load of the pipework at installation temperature before the system is operational. In the factory, the coil is pre-compressed to this cold load and held in that exact position using 2 or 3 preset stops. These preset stops are painted red, so they're easy to identify on site, and so you know not to remove them until the unit is fully installed and the load is properly transferred. Brad, when would there be 3 preset stops?
Thanks, Riley. Yeah, 3 preset stops will be used when there is a very large load, and these will be on the size 18 to 22.
Okay, that's good. So on the outside of the spring can, you can see a scale plate. This has 2 markers. You can see there's a blue marker, which represents the cold or preset position. And there's also a red marker, which represents the hot or operating position of the spring when the system is at temperature. When the plant becomes operational and the piping system expands, the load on the spring changes. As a result, the spring either compresses or releases slightly, and you'll see the indicator move from the blue mark toward the red mark. That will show that the spring is doing exactly what it's supposed to do. It's absorbing that load change and allowing the pipe to move freely without transferring excessive stress onto the system.
All our spring supports are sent with a scale plate. However, in time, they may, due to corrosion, fall off or there will be an issue. We would recommend you to contact Binder Group for advice.
A correctly functioning variable spring support will always move smoothly between these cold and hot positions as the system cycles. Now that we understand how variable spring support works at a basic level, we're going to move into how to choose the right support for your application. So we're going to start by looking at the different spring types and how each configuration is intended to be used. One of the most important things to understand up front is that the type of spring doesn't change the spring's internal mechanics. A type A and a type F, for example, both contain the exact same spring coil and performance characteristics. What changes is how the can is oriented. In other words, the spring type is more about geometry and mounting, not spring behavior. So let's look at the two major families, hanger types and base mounted types. Base mounted springs are used when the support sits below the pipe, working in compression to push upward. These are widely used under pipe shoes and structural supports. The type F is the standard base mounted design. It can be supplied with an optional PTFE slide plate to accommodate axial and or lateral movement. They're used anywhere the pipe sits on a shoe or a support beam and needs vertical flexibility while sliding axially or laterally. Roger, when is a PTFE slide plate typically used?
Yeah, we'd typically see a slide plate used where there's a moderate amount of movement, either axially or laterally. And that would be typically a small amount of movement, say less than half of the length of a shoe, the pipe shoe. And that's to just allow for smooth movement without putting any pressure on the support or the pipe. The other use for a slide plate is to actually act as an isolator between dissimilar metals. So you might have a galvanized load plate and a stainless steel or duplex pipe, and you just want to create a barrier between those to save any dissimilar metal corrosion. Now, there's a higher axial movement is needed. There's other options which we'll cover shortly.
Yeah, it's good. It probably comes up here. So the type H incorporates a curved cradle that sits directly under the pipe. It's typically used for smaller diameter lines where no pipe shoe is installed. The design is intended to keep the pipe centered and also avoids point loading on that pipe. The type K, probably more what you're referring to there, Roger, includes a roller to allow controlled axial or lateral movement, and it's a preferred option for long straight runs where the pipe may shift horizontally due to expansion. Hanger springs are used when the support is mounted above the pipe and the spring works in compression through a hanger rod. These are the most common types where pipes run along elevated steel. Type A connects to a threaded hanger rod with adjustment made via the turnbuckle or rod connection. You'll typically see this wherever there is clear overhead steel and enough headroom to hang the support directly above the pipe. Type B, this uses a lug and pin connection at the top instead of a threaded rod. This is useful when the structural steel only allows for clever style attachments or when some lateral movement of the pipe is expected. Generally speaking, type B and type C that I'm about to cover are the more common types of hanger springs that we see used. So type C includes a clevis and pin assembly, and that allows more lateral movement than type A or B. If a pipe is expected to swing slightly due to thermal effects, or if alignment between the hanger rod and spring can't be perfectly straight, you'll generally see a type C used. Types D and E are designed for installations with limited headroom or where the spring is mounted directly onto structural steel. They're often used in retrofit projects or tight corridors where a traditional rod hanger won't fit. Roger, what's the difference? Where would I want to use a type D or a type E over the other?
Yeah, thanks. The difference is mainly in just how the load is taken up via the threaded hanger components in the rest of the support system. So with a Type D, the thread actually comes right through the spring and the load is taken by a nut and washer on top of that little tube you can see. And Type E, it's the same principle, but the load is taken at the point of the load plate, which sits just above the spring, inside the canister. And Type E would be typically used where you've got a really congested area, you've got very limited headspace, and it's not as easy to adjust. Type D is easy to adjust. The nut is external. Adjusting nut is external to the spring, whereas the Type E, you may need a special spanner, or it's just a little bit more fiddly to adjust, but necessary when there's limited room.
It's good. Type G is a very distinct configuration. So this uses two spring cans connected by a trapeze, supporting the pipe from below, but while still being hung from above. And so where would you see these used normally, Roger?
Typically, they'd be used when there's really high loads, or very large pipes suspended, where there's a pipe shoe involved. So the pipe's supported by a shoe. The shoe is then supported by this trapeze, or where there's a saddle needed, as we can see in the top left there. But typically high loads where there's some form of movement allows the spring allows it to swing a little bit. Not that we're trying to rely on that, but it is slightly flexible in all directions.
That's good. So typically we find that an engineer's choice of support type is driven by sort of 5 key factors. First being where the structural steel is in relation to the pipe, whether the pipe is going to be supported from above or below, whether there's any axial or lateral movement that needs to be accommodated. If there's limited headroom, how best to use what best type to use where there's limited space. And then if there's a shoe or a cradle or something structural already connected to the pipe, what type is going to work with that. So once the type is decided on, the next step is usually choosing the right size and the right travel range. And that comes down to the load, movement, and the 25% variability rule. So we're about to cover off on that. So on top of these things, load, movement, variability, we also need to consider things like corrosion protection and then the right mechanical interface for the environment it's going to operate in. In practice, the size selection follows the same general pattern. For this, we need 3 key pieces of information. First, we need the hot or cold load in either newtons or kilograms. This is the sustained operating load on the support, and it must include the pipe, insulation, contents, fittings, any other permanent attachments. We want to use the actual sustained weight, so not a nominal figure. Second, we need the vertical movement of the pipe at that support point and the direction, so whether the pipe moves up or down from cold to hot. This will come from the pipe stress model or the design drawings. Third, we'll need the travel range series, so BV35, BV70, BV140, so on. The naming's simple, so the BV35 supports up to 35 millimeters of movement, BV70 up to 70 millimeters, so on. Generally, to procure these supports, we would ask that a request form is completed. This is downloadable from the Binder website. Brad, do you want to just take us through the different components here of the load table?
Sure. Yeah, first you can see at the top of the screen is a yellow box. These are the load ranges, so from size 0 all the way up to size 22. The red box is the working range of each spring support from the 0 to 22 sizes. And then to your left is the green box. This lists the travel ranges of the 4 sizes that we can offer, so BV35 up to BV210. And then down the bottom, you'll see the blue box. This is the spring rate of each spring, so from size 0 to 22, and also from BV35 up to BV210.
Virtually all major piping standards will limit the acceptable load variation between the cold and hot condition to 25% or less. So this ensures that the spring support conforms to design standards, but it also ensures that it doesn't overload the pipe. The formula to calculate this is fairly straightforward. Typically, the variability percentage is equal to the movement multiplied by the spring rate multiplied by 100 over the hot load. The spring rate comes directly from the Binder load tables Brad just showed us before. So generally, if the calculated variability for any given spring exceeds 25%, the solution is usually to go up to the next spring series. So, for example, going from a BV35 to a BV70, or from a 70 to a 140. The higher series springs will have lower spring rates, which reduces the load variability for the same amount of movement. So if we were to go through a simple example, say we had a hot load of 10,789 newtons. We would look at the load chart, find where the load is. So in this case, we've actually got a size 12. We also have 20 millimeters of movement upward, which needs to be considered. So we would be looking more at a BV70. 20 millimeters here is almost going to top out on a BV35. So we're looking at a BV70 here. And the spring rate for a BV70 at size 12 is 79 newtons. So to calculate our variability, we're going to get our movement, 20 millimeters multiplied by our spring rate of 78.8 newtons, multiplied by 100 over our hot load of 10,789 newtons, which is a 14.6% variability, well within limits according to design standards. From here, you can calculate what we call the calculated preset load. So that is equal to the hot load minus the movement multiplied by the spring rate. So in this scenario, 10,789 newtons minus 20 multiplied by 78.8 is 9,213 newtons. And so if this spring was going to be installed when the system is not operational, so at a cold load, you'd need to get this preset to 9,213 newtons. It's important to check both the preset load and the available travel during selection, ensuring the spring doesn't bottom out or exceed its working range. Once the correct size and travel range are selected, the last piece is choosing the right materials and coatings for the installed conditions. We need to consider the environment the support will be in. These conditions will determine the coatings, housing type, and optional materials you may need. Roger, do you want to take us through these different coating options?
Yeah, sure. The coating options are generally determined by how aggressive the environment is around the spring. So very standard is acrylic painted. We'd have a neoprene coating, often for marine environments, or even a plastic or polymer powder coated system on that as well. The casing and load plates, hot dip galvanizing is most common, but again, where the environment is more aggressive, say for marine or in a chemical plant, an epoxy paint system is often used. Custom paint spec or standard system that we have, or we can just supply it as blasted and primed for painting on site. There's also the option of stainless steel, and that would be most common on marine or in a chemical plant, that sort of application. The threaded load tube would be most typically galvanized or stainless steel. On very small springs, we may use a zinc plated option or even just custom coatings. Like in that top right, you can see a green load plate. That's actually a Xylan coating, which is a Teflon variant, and that's very high in resisting corrosion.
It's worth noting that choosing the right coating is not just about preventing rust. So corrosion can cause all sorts of issues, binding the pressure plate. In some severe cases, it'll actually freeze the spring entirely. Good protection will extend the life of the support and helps to ensure consistent travel through its operating life. So now that we've covered off on the selection of appropriate springs, let's look at performance, installation, and maintenance. So first, we'll talk about how they arrive. So our units are shipped in a preset or locked condition, specifically to ensure safety during shipping and accurate installation. So that means that the internal spring coil has been compressed to the designated cold load and is held in place by preset stops. These are painted red to make them easily visible in the field. They're in place so that during hydrostatic testing or transport, the spring doesn't move and the rigid components take the test load instead. Brad, just a quick one here. Is the spring always set to the cold load?
Most of the time, probably about 95% of our spring supports are supplied preset to the cold load. However, there will be some times that the site cannot shut down the line, and that means we would have to supply a spring support preset to the hot load.
Okay. So before we install the support, we want to confirm the unit's nameplate and tag match the drawings. So the correct model, correct size, the correct load. This is something we do ourselves when manufacturing in accordance with drawings. But when there are various sizes and types procured at any given time, we want to make sure that we use the right springs in the right places on site. When the support is mounted, remember that the preset stops must remain in place until the piping load has been fully transferred to the support. Don't remove them too early. Quickly with load transfer, the method that you use depends on how the support is mounted. So for hanger types that are suspended above the pipe, the load transfer is typically achieved by adjusting the turnbuckle on the hanger rod. So adjusting this will slowly shorten the length of the thread and cause the spring coil to compress and then transfer the load smoothly onto the spring. For base mounted types, the load's transferred typically by turning the nut on the low column on top of the spring housing until the pressure plate contacts the piping system and takes the pipe load. Once the load is supported and you've satisfied the load is now carried by the spring support, you can remove the preset stops. This unlocks the coil so it can move during operation. Brad, how do we know when the load has been properly transferred?
This is quite important. When you know is when the preset stops become loose by the hand. So as you touch the preset stops, if they are loose, then you know that the load has been reached and you can remove them by hand.
Yeah, that's good. So after preset removal, we want to check the indicator alignment. So the underside of the pressure plate should align with the blue cold load marker on the scale plate. This confirms that the unit is now in its correct installation position and is ready for normal hot cycle movement. If it's not aligned, you need to adjust the turnbuckle or load nut until it is. In larger systems, especially extensive pipe runs, you typically want to follow a logical sequence. For horizontal runs, installation should generally proceed from fixed supports outward to the free supports. This ensures the load path is consistent and you don't inadvertently shift loads. For vertical systems, installation usually starts from the top down to maintain stability and avoid unsupported spans. It's critical to emphasise one key point. If the preset stops cannot be removed by hand, you must continue to adjust the load onto the spring support. Do not use mechanical devices to forcibly remove the stops. So let's recap the main procedural steps. We want to verify we've got the correct unit. We want to mount the support, but keep the travel stops engaged. Transfer the load using the turnbuckle or the pressure plate nut. Once the pipe load is carried by the support, you can then remove the preset stops. Confirm the indicator aligns with the blue cold mark and follow proper sequencing for installation. But never overlook those preset stops. They are in place for a reason. Anything you'd like to add there, Rog?
Only just to reiterate that last point, there's a lot of tension stored in that spring in its cold position. So you might have a spring that's designed for 20-ton load. It's got a 200 mil travel. If that is let go in error, you've got a lot of released energy uncontrolled, and we just don't want to hear about any accidents or incidents that are caused. So that's why we're taking that point up strongly, just to ensure that people are aware of the danger involved there.
That's good. So with the installation covered, we're going to move on to how to verify performance in the field. In practice, the easiest and most reliable way to verify performance is to look at the indicator plate on the side of the spring. When the system is in its cold condition, typically at or near ambient or during shutdown before startup, the underside of the pressure plate should align close to that blue cold load marker. That's the position the spring was preset to at the factory and adjusted to on site. When the system heats up and the pipe expands, the spring will compress or relax accordingly. When that happens, you should see the indicator move smoothly away from the blue marker toward the red marker. That visible movement between cold and hot positions is one of your best confirmations that the spring is supporting the load correctly while the pipe moves. So there's really three simple questions to ask from a field check standpoint. Firstly, is the indicator where I expect it to be when the system is cold? Does it move into the expected range when the system is hot? And is the total movement consistent with what the design said it should be? If the indicator doesn't move at all between cold and hot conditions, it's usually a warning sign. So it can mean several things, but it could mean that the spring is seized due to corrosion, dirt, or debris. It could mean the pipe isn't moving as designed, or the load is shifted onto some other support. Industry guidance emphasises checking both the physical integrity of the assembly and the position of the spring coil or indicator against the original design data sheets. If the indicator moves too far, for example, it's right at the upper or lower end of the scale, that can indicate the spring is undersized, overloaded, or maybe it's been adjusted incorrectly. In extreme cases, the coil may actually bottom out, which means it's fully compressed and cannot deflect any further. So that's a serious condition because the support has essentially become rigid and can't accommodate further movement. In those situations, the support system should be reviewed to decide whether the field adjustment or complete replacement is required. If the indicator is off scale, so nowhere near either the blue cold position or the expected hot range, that can often point to either the wrong preload, incorrect installation height, or field adjustment that's been done without reference to the original settings. Can usually be adjusted by going back to the cold position, re-establishing the correct cold load using the turnbuckle or adjustment nut, and then verifying that the indicator matches the blue marker again before returning the unit to service. It's also good practice to compare the actual travel you're seeing on the indicator with the travel that was specified on the drawings or support data sheets. If what you see in the field is significantly different, either the piping isn't behaving as expected or something has changed over time. It could be extra weight added, supports locked, or maybe some piping modifications done without updating the springs. During major shutdowns, you can do a simple check by walking the line when everything is back near ambient. Most, if not all, of variable supports should be close to their cold position again. If a spring is still sitting near the hot end of the scale when everything's cooled down, it may be binding, it could be misaligned, or it's carrying a load it wasn't intended to carry. So there's a few quick visual checks that do go a long way. So look for uneven or skewed movement. The pressure plate should move straight, not rub heavily on one side of the casing. The sign of this is where the spring casing is not sitting vertically. Check for corrosion and built up dirt or debris around the slots where the indicator moves. Anything that can jam that movement should be cleaned. It might need to be recoated properly. Make sure that any packing straps or items that were meant only for shipping or hydro test haven't accidentally been left engaged. If you combine these simple checks and a quick comparison to the original design data, you should get a pretty good picture of whether the variable spring supports are still functioning as designed across the whole system. Brad, in your experience, are there any other practical tips around maintaining these that we should highlight?
During installation, care is sometimes not really a concern, and the casing can be damaged or scratched, so that means the paint or the galvanizing can be removed. This can lead to corrosion. So I recommend after you've installed the spring support is to touch up the surface protection. And this is, we see this all the time, that it doesn't get done and it leads to accelerated corrosion. So yeah, we recommend to keep it clean and also the corrosion protection fully maintained.
It's good. Alrighty, let's take a look at what it takes to keep these supports reliable and safe over the long term. So in good news, it is that the variable supports, they're generally low maintenance by design. The coil is fully enclosed within the can and there's no internal servicing requirements. This is consistent across all the Binder variable supports. The spring itself should never be removed or dismantled in the field. It's under compression, and disassembly requires specialised equipment at the factory. So the focus of field maintenance is usually about the external components and ensuring the spring can move freely. Routine checks are usually carried out during planned shutdowns or annual inspections. These checks are simple, but they're important. The first thing to look at is the condition of the protective coating, to your point, Brad. For standard units, that's typically hot dip galvanizing. For harsher environments, it may be a multi-coat epoxy system. Any damaged or worn coating should be cleaned and touched up as needed. Corrosion is one of the main issues that interferes with smooth spring movement, so it's critical to check for. You should also check that the spring has unobstructed vertical travel. The pressure plate must be centered and able to slide smoothly inside the casing. Check the threaded components, turnbuckles on hanger types, or adjustment nuts on low columns for the base mounted types. These should be lubricated periodically with suitable grease, and that'll allow adjustments to be made in future without galling or forcing the threads. A few key points to bear in mind here. Never dismantle a unit. Springs under compression and removing internal components can be dangerous. Before removing a support from service, make sure to reinsert the preset stops back into the unit in the cold position. This prevents any unexpected movement once it's disconnected. And finally, always support the pipe independently before unbolting the spring support. A sudden shift in load can damage the piping or injure personnel as well. All right, before we move into questions, I want to just wrap up today's session with a quick summary of what we covered. So we started by looking at how to select the right type of spring support, gone through how to choose the correct type, the right travel range, appropriate materials, how to apply the 25% variability rule so that your support will perform the way it needs to. From there, we've looked at how to confirm that your spring supports are performing correctly in the field. So check your movement, recognise signs of incorrect behaviour, understand what proper cold and hot positions look like. And then we've also touched on installation, maintenance and safety. And with that, we're going to answer a few questions. All right. Roger, have you had a bit of a look at that?
There's one that's come through earlier about how to safely remove a spring support that's in service. I think we covered it briefly, but it's important to make sure that the pipe is supported independently of the spring support, and then you can take the load up with the threaded load tube, insert the chocks, the load blocks in there, and then it can be unbolted or removed from the structure or from the floor and taken away. But just make sure those chocks are in the support and strapped in, preferably, even if it's just tied in somehow. We don't want those rattling free. There's another one about frictional reaction. As the pipe moves, does it produce much of a frictional reaction on the pipe support? That is a classic for where we'd recommend a Teflon slide plate. So that'll just allow that movement to save transferring any horizontal or other directional load onto the support. We have another interesting one from Jason on where site welding is not allowed. So it's a vibrating environment. Vibration's always a hard one to get around. Wherever there's threads, obviously they'll need to be locked up with lock nuts or whatever any other approved thread locking system that you're using on site. So if you're using a BG220 beam clamp with a plate, and then it'll be bolted to the structure, I'd suggest probably using a type B and make sure that it's a pin with split pins, not a threaded connection there. Some vibration is actually taken out by the spring, but as long as the threads are locked up, I think that's probably as much as you can do. Is there any comment you'd have on that, Brad?
What you've covered is pretty much, a recommendation to maintain the bolts uptight, so don't come loose.
And there's you can also put a rubber membrane in between the pipe and the clamp, and that will help just absorb some of that vibration as well. That's quite common.
For hanging components where you can't use a welded hanger connection at the top, it is possible to supply these with a plate pre-welded to them and bolt holes through it so that it can be bolted on site. Basically, we would do the welding in-house. I'll just take this one from Michael in relation to the larger unit being selected. Michael, just to answer your question there, the numbers are purely hypothetical. At 10,789 newtons, we sort of pulled that out of the air. So typically speaking, these load charts are there to be read based on whatever hot load you have with your particular project. So sometimes it's a very, very light load in the overall scheme of things, and that means you'll be going much lighter size of spring. Now, there are some cases, some overlap in what springs can be used, and it's dependent on the amount of movement. Now, Brad, any comment there on that one?
Yeah, generally, with the amount of movement, you can go with a BV35, and that is generally the cheapest. However, with the variability, that can be above 25%. So then we would recommend to go with the BV70. But just to add to what Riley said, is that we don't choose the size. It's purely based on the load data that the clients provide us. So as Riley said, the load range is limited to a certain range, which dictates the size.
It's good. Thanks. This is an interesting one, Rog, from Alexandra, about can the hot load be the sustain load when the piping is not in operation?
And you're probably the most knowledgeable on that one.
If the hot load and the cold load are within the working range of the spring support, then yes, both of them can operate. But if your hot load is outside the range, then no, that's not possible.
Is it potentially a case where a multi-lock could be required?
Yes. A multi-lock. So our standard variable spring support has preset stops, and they can only relock the spring support at the cold load or the original load that was locked in the factory. If you do want to lock the spring support at any operating load throughout the working range, then we recommend you purchase a spring support, what we call is a multi-lock. So you can lock it at any range. It is a little bit more expensive, but we believe it adds a lot more value because you can lock it at any operating load.
Probably a topic for a future webinar, eh, Brad?
Yes, true.
We've got about a minute or two left here. Aaron's put a question in here. So talked about the adjustment of the spring hangers when they're being installed by turning the turnbuckle or nut, depending on the spring support configuration. How do you do this with Type B configuration if you don't use a turnbuckle?
The Type B does come with a turnbuckle. A Type E sometimes isn't provided with a turnbuckle. So the adjustment would be done at the top of the casing. There is limited movement, but there is enough adjustment of the hex nut at the top to transfer the load onto the spring support, and then you can safely remove the preset stops.
That's good. There's a number of other questions here, but we've run tight on time. So what we will do is we'll circulate a bit of a FAQ document of the questions that have been in here and some of the answers for everyone to look at. We very much appreciate everyone's time and would be very interested in your feedback too on our first session in this technical webinar series. Thanks all for joining.
Thank you.
Yes.